Introduction to Prolog. Welcome to Introduction to Prolog. Prolog stands for Programming and Logic. This language is fundamentally different from most programming languages you may have encountered. Instead of telling the computer how to solve a problem step by step, you describe what you want to achieve, and Prolog figures out how to do it. Prolog is a logic programming language with deep roots in artificial intelligence research. Today, we'll explore what makes Prolog unique, how it works, and where it's used in the real world. Prolog is a declarative logic programming language created in the 1970s. Unlike imperative languages like C or Java, Prolog is based on formal logic. You don't write sequences of instructions. Instead, you define facts and rules about your problem domain, then ask questions. The core concept is simple. You tell Prolog what you know, and you ask Prolog what you want to find out. Prolog uses a built-in theorem prover to search for solutions. It's particularly powerful for problems involving symbolic computation, pattern matching, and complex relationships. Prolog originated in artificial intelligence research, specifically in natural language processing and automated theorem proving. It remains one of the most popular logic programming languages today. Prolog was created in 1972 by Alain Conrauer and Philippe Roussel at the University of Aix-Marseille in France. The name is an abbreviation of programmation and logique, which means programming and logic in French. Originally, Prolog wasn't intended to be a general-purpose programming language. It emerged from a project aimed at processing natural languages. The creators were trying to develop tools for automated theorem proving and computational linguistics. The language was influenced by Robert Kowalski's procedural interpretation of Horn clauses, which provided the theoretical foundation. In 1977, David H. D. Warren developed the first compiler for Prolog at the University of Edinburgh, creating what became known as Edinburgh Prolog. This syntax became the standard used by most modern Prolog implementations. The first ISO standard for Prolog was published in 1995, establishing a formal specification for the language. Prolog has 4 key features that distinguish it from other programming languages. First, unification. This is Prolog's pattern matching mechanism. Unification tries to make 2 terms identical by finding appropriate substitutions for variables. It's more powerful than simple assignment or equality checking. Second, backtracking. When Prolog encounters a dead end in its search for a solution, it automatically backtracks to try alternative paths. This systematic search strategy is built into the language. Third, recursion. Prolog uses recursion as its primary control flow mechanism. Instead of loops, you define solutions in terms of themselves. Recursion is fundamental to how Prolog programs work. Fourth, single data type term. Prolog has only one data type, called a term. Everything in Prolog is a term, whether it's a number, an atom, a variable, or a complex data structure. Prolog has 4 types of terms. Atoms are symbolic constants. They begin with a lowercase letter or are enclosed in quotes. Examples include John, red, and hello. Atoms represent fixed, unchangeable values. Numbers can be integers or floating point values. Most Prolog implementations support arbitrary precision integers, meaning you can work with very large numbers without overflow. Variables begin with an uppercase letter or an underscore. They serve as placeholders that can be bound to any term during program execution. Variables in Prolog are similar to variables in mathematical logic. They can only be bound once, making them single assignment. Compound terms are the most complex type. They consist of a functor, which is an atom, followed by arguments, which are also terms. For example, parent, John, Mary, is a compound term with a functor parent and 2 arguments, John and Mary. Lists are one of the most important data structures in Prolog. A list is written as comma-separated elements enclosed in square brackets. For example, you can write a list of fruits as open bracket, apple, comma, banana, comma, cherry, close bracket. Prolog uses the head-tail notation to work with lists. The first element is called the head, and the rest of the list is called the tail. You can access them using the vertical bar operator. For example, if your list contains apple, banana, and cherry, Then the head is apple, and the tail is the list containing banana and cherry. Lists can contain mixed types, including other lists. The empty list is written as open bracket, close bracket with nothing in between. Prolog provides powerful built-in predicates for working with lists. Common operations include checking if an item is a member of a list, finding the length of a list, concatenating two lists together, and sorting a list. List processing in Prolog relies heavily on recursion and pattern matching. Prolog programs are built from three fundamental constructs: facts, rules, and queries. Facts are assertions about the world. They declare that something is true. A fact consists of a predicate name followed by arguments in parentheses, ending with a period. For example, parent John Mary states that John is a parent of Mary. Rules define relationships between facts. A rule has a head and a body separated by the symbol :dash, written as smiley face, which can be read as if. For example, grandparent X, Y, parent X, Z, parent Z, Y. Means X is a grandparent of Y if X is a parent of Z and Z is a parent of Y. Queries are questions you ask the Prolog system. They begin with $dash, written as, for example, grandparent John asks, who are John's grandchildren? Prolog will search through the knowledge base and return all matching solutions. Let's look at a classic example: calculating factorials using recursion. The factorial of a number is the product of all positive integers less than or equal to that number. For example, the factorial of 5 is calculated as 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1, which equals 120. In Prolog, we define factorial with two clauses. First, the base case, fact 0. This states that the factorial of 0 is 1. Second, the recursive case, fact nf, n greater than 0, n1 is n1, fact n1 f1, f is n asterisk f1. This reads as, the factorial of n is f if n is greater than 0, n1 is n minus 1. The factorial of n1 is f1, and f is n times f1. To use this, we query. Fact 5 result. Prolog returns. Result equals 120. This example demonstrates Prolog's natural approach to recursion. We don't need to manually manage the stack or control flow. Prolog handles the backtracking and recursion automatically. The family tree example demonstrates how Prolog handles relationships. We start by defining facts about gender and parent-child relationships. First, we define who is male and who is female, male Jack and male Oliver, for males, and female Helen for females. Next, we define parent-child relationships. Parent underscore of Jack, Jess, means Jack is a parent of Jess. Then we create rules for more complex relationships. For example, father underscore of X, Y, male X, parent underscore of X, Y. This states that X is the father of Y if X is male and X is a parent of Y. We could define even more complex relationships. Grandfather underscore of X, Y, male X, parent underscore of X, Z, parent underscore of Z, Y. This creates a chain of relationships. Now we can query our knowledge base. Grandfather underscore of Jack. Prolog will find all grandchildren of Jack. We can also ask sibling Jess to find Jess's siblings. This example shows how Prolog excels at representing and querying complex relationships. The n-queens problem is a classic puzzle in computer science. The goal is to place n-queens on an n by n chessboard so that no two queens attack each other. This means no two queens can be in the same row, column, or diagonal. For the 8 queens version, there are 92 distinct solutions. For larger boards, finding solutions manually is nearly impossible, but Prolog can solve it efficiently. Here's a Prolog solution using constraint logic programming. N-by-queens, n, qs, lent, qs, n, qs-ins1, n, safe underscore queens, qs. This defines a list called qs of length n, where each element is between 1 and n, representing the row position of the queen in each column. This safe_queens predicate uses constraints to ensure no queens attack each other. It checks that no two queens are in the same row, column, or diagonal. To find a solution, we query n-queens, 8 queens. Prolog returns a solution like queens equals 4, 2, 7, 3, 6, 8, 5, 1, where the first number represents the row of the queen in column 1, and so on. This example demonstrates Prolog's power in solving combinatorial search problems with minimal code. While Prolog is primarily declarative, it provides mechanisms for controlling the search process. The cut operator, written as an exclamation mark, is Prolog's primary control mechanism. It commits to the choices made since its parent goal, preventing backtracking. This can improve efficiency, but reduces the declarative nature of the code. For example, in a maximum function, max x, y, x greater than y, the cut prevents Prolog from trying the second clause if x is already greater than y. Negation as failure is another control mechanism. The predicate not goal succeeds if goal fails. It's used for expressing negative conditions. For example, not member x list succeeds if x is not in the list. In modern Prolog, you'll often see a backslash followed by a plus sign instead of the word not. They're equivalent. Use the cut sparingly. While it can improve performance, it can also make code harder to understand and debug. Purely declarative Prolog code is generally preferred. Prolog has been used in various real-world applications, particularly in artificial intelligence and complex problem-solving domains. IBM Watson used Prolog for pattern matching over natural language parse trees. Watson's developers stated that Prolog was the ideal choice for the language due to its simplicity and expressiveness in handling complex language patterns. Expert systems use Prolog to encode knowledge as facts and rules. Applications include medical diagnosis systems, legal reasoning tools, and financial advisory systems. Natural language processing was one of Prolog's original applications. It's used for parsing grammar, semantic analysis, and language understanding tasks. Database systems benefit from Prolog's query capabilities. TerminusDB, an open-source graph database, is implemented entirely in Prolog. Automated theorem proving leverages Prolog's logical foundations. It's used in mathematical proof verification and formal verification of software. Other applications include scheduling, planning, robotics, bioinformatics, and knowledge representation systems. Several Prolog implementations are available, each with unique features. swi-prolog is the most popular and widely used. It's free, open source, cross-platform, and has extensive libraries. It's recommended for beginners and experienced programmers alike. GNU Prolog is a native compiler with a constraint solver over finite domains. It's fast and efficient, with strong ISO compliance. SICStu's Prolog is a commercial implementation known for high performance and robustness. It's used in industrial applications. Scryer Prolog is a modern implementation focused on ISO compliance and advanced features. For development tools, VS Code extension provides syntax highlighting, debugging, and IntelliSense for Prolog. Swish is a web-based Prolog environment that requires no installation. Emacs Prolog Mode offers advanced editing features for Emacs users. Most implementations also provide interactive development environments with debuggers, tracers, and profilers. Like any programming language, Prolog has strengths and weaknesses. Advantages: conciseness. Prolog programs are often much shorter than equivalent programs in other languages. Pattern matching. Built-in unification provides powerful pattern matching capabilities. Automatic backtracking. The search mechanism is built in, eliminating the need to implement it manually. Knowledge representation. Prolog naturally represents facts and rules, making it ideal for knowledge-based systems. Rapid prototyping. Complex relationships can be defined quickly and tested interactively. Disadvantages. Performance. Prolog can be slower than compiled languages like C for sequential, deterministic computations. Learning curve. Thinking declaratively rather than imperatively requires a paradigm shift. I/O complexity. Input-output operations are less straightforward than in imperative languages. Debugging difficulty. Tracing through Prolog's search trees can be challenging. Limited mainstream adoption. Prolog is not widely used in industry, which can limit library support and community resources. For those who want to dive deeper into Prolog, here are the key resources used in this presentation and recommended for further learning. Primary sources. The core information about Prolog's history and features comes from the Prolog Wikipedia article, which provides comprehensive documentation of the language's development and standardization. Additional technical details were gathered from the swi-prolog official documentation and the Geeks for Geeks Prolog tutorial series. Academic references. For the historical and theoretical foundations, this presentation draws from several key academic papers. These include Alain Komarauer's seminal work on the birth of Prolog from 1972, Robert Kowalski's work on the procedural interpretation of horn clauses, and David Warren's papers on the Edinburgh Prolog compiler of the Warren Abstract Machine. Books and learning resources. For comprehensive learning, the classic textbook Programming in Prolog by Klocksin and Mellish remains an excellent reference. The Art of Prolog by Sterling and Shapiro provides advanced techniques. For those specifically interested in AI applications, Prolog Programming for Artificial Intelligence by Ivan Bratko is highly recommended. Online resources and tools. The swi-prolog website, swi-prolog.org, offers complete documentation, tutorials, and a free download of the most popular Prolog implementation. The Learn Prolog Now website provides interactive lessons. For hands-on practice without installation, swish. swi-prolog.org offers a web-based Prolog environment. Community and support. Active Prolog communities exist on Stack Overflow and Reddit, where you can ask questions and find solutions. The swi-prolog mailing list and GitHub repositories provide additional support and code examples. These resources will help you continue your journey into logic programming and Prolog development. Prolog offers a fundamentally different approach to programming. Instead of specifying how to solve a problem, you describe what you know and what you want to find. This declarative paradigm makes Prolog particularly powerful for problems involving complex relationships, symbolic computation, and search. While Prolog may not be the best choice for every application, it excels in specific domains like artificial intelligence, expert systems, natural language processing, and constraint solving. Its unique features, unification, backtracking, and declarative syntax, enable elegant solutions to problems that would be complex in imperative languages. The language continues to evolve, with modern implementations like swi-prolog and swi-prolog offering improved performance and features. If you're interested in logic, AI, or simply want to expand your programming horizons, Prolog is worth exploring. Thank you for your attention. I hope this introduction has given you a solid foundation for understanding and working with Prolog.